Okay, and let's welcome Wanseob.
Today I'm going to talk about the Schnorr-based sequencer, which is a commitment scheme mostly for layer 2 solutions. I am Wanseob and working at the PSC team as a researcher. Let's start. Nowadays, mostly for the layer 2s, we should think like we're gonna commit optimistically and then verify them cryptographically. So maybe many of the teams are trying to use this approach, like separating the commitment scheme and the verification scheme. And what I want to talk today is about the commitment scheme. Mostly when we commit some layer 2 transactions on chain onto the layer 1, we usually commit a batch of transactions. We collect many transactions and create a batch and commit that onto the layer 1. But the problem here is that it is not that suitable for low throughput roll-up chains. For example, you launched your own smart contract and then you want to run your own roll-up. But mostly, specific smart contract does not have a big throughput. For example, like 0.1 transaction per second. So if that, it'll take like more than a few minutes or more than few hours to commit a batch transaction. So what we can do here is commit a transaction instead of committing a batch of transaction. Then what we can expect from here is that having a instant finality for every transaction and executing the state transition for every transaction right away. Let's see how we can achieve this. Simply, we're gonna let the sequencer give a signature for every transaction index. Which means when you submit a transaction, you sign a signature, but also you are gonna get a signature from the sequencer too. So we are completing one signature as using the multi-party computation from the user side and from the sequencer side both together. And the Schnorr signature is one cryptographic scheme which satisfies what we want to do here. Using the Schnorr signature, to be a little bit specific, to be more detailed, the sequencer and the sender complete a signature for a specific transaction index. So by this signature, the sequencer is committed to including that transaction into the given index onto the layer 1 chain. Which means if you have that signature, later then the sequencer, if not include that transaction to that given index, then the sequencer will just slash it. And to achieve an instant finality and the instant state transition system, actually we have to have a data layer by constructing a peer-to-peer network each other. So for example, if I'm a node and if I have all the Schnorr signatures for the given indices, for example, from index 1 to index 173, then I can instantly execute all the transactions from index 1 to index 173. So it enables the transaction level commitment model. So what do we expect here is simply we want to do some instant state transition, and also we want some application specific rollups which have some low throughputs. Okay, now we're gonna start about the cryptography, and it's really the not that difficult. So it's your starting point, and I'm pretty sure that you're gonna make some fun just following the cryptographical setup of how the Schnorr signature works. Okay, let's start. So don't worry. Schnorr signature is one of the most simplest scheme of the elliptic curve cryptography. Let me explain you step by step. So we're gonna, would you mind if I sit down here? Okay. So you might be pretty familiar with the signature itself, right? So here, for example, and also public key and the private key. In this setup, this small k is your private key. So if you multiply your private key to a certain elliptic curve point, then it becomes another point. And that is P, which is your public key. So to sign to some challenge, which is E, using your private key, then you can just simply multiply your private key and also the challenge scalar value to a certain point, actually which is called generator. Then you are gonna get another point, which is SG. And then only you can generate this small s value because you are the only one who knows small k. So this s becomes E times k. But actually here is a problem. The problem is if you know the small s and if you know the small e, you can simply calculate the private key just by dividing them, because k equals s over e. So to prevent this key retrieval from the signature and the challenge, we add a random salt here, and this is called the random linear combination method. So we have a small r, which is random value, and if you add some random point here, then actually people cannot retrieve your private key even if they do not know the random salt you made here. And actually, to protect your private key securely, you should not share your private random value with others. So this is how the Schnorr signature works. And in more detail, to sign a message, usually we just do like this. Alice have a private key K and public key P, and has a message to sign, which is M. And then we compute the challenge value E using the hash of the, before that, we choose a random nonce to keep the private key securely, which is small r, and its public value large R, which is a multiplied by R, the generator point. And then we compute the challenge value small e using the hash of large R and the public key and the message, and it becomes the challenge. And then create a signature using s equals small r plus your private key times e. And then finally shares your small s value and public nonce large R value with others. Then this is how Schnorr signature works. And actually there are some pros and cons of this Schnorr signature. If you have ever just took a look at the ECDSA, you just feel like, oh, actually this looks pretty simple and pretty easy. Then that reason is because it is using only the addition here. So Schnorr signature has an additive homomorphism. That is a pros, and also it becomes a cons. Because it has a additive homomorphism, we can simply cancel the key. Like choosing a minus other people's public key value to my random nonce value will cancel others' public key. So which means like you and me complete a Schnorr signature together just by adding our two signatures. But if I set some value, just minus your public key, then actually I can cancel the opposite signature. So that is called key cancellation attack. So to prevent the key cancellation attack, we can use the mu-sig approach, which is multiplying some weight factor to the each public key. So this is about how to complete a signature together by two parties using mu-sig protocol. It is something having my own weight factor and the opposite's own weight factor and multiplying the weight factor to the public key. So it will prevent some other one cancel my signature by just subtracting some public key value. So music works like, let's say we have Alice and Bob. Alice have a private key, Bob also have a private key, and Alice's public key PA equals KA times G. Bob's public key PB is KB times G. And also they both pick their own random nonce value, which is small r A and the small r B. And then we can simply calculate its public random nonce value, large RA, which is RA times G, large RB, which is RB times G. And then we start to compute the weight factor for each other. So aggregate the public nonce and compute some public keys, hash of the public key set, and compute some weight factor using hash that value. So there's not some complex logic to compute the weighted factor. The only one thing we want to achieve here is just making deterministic, making the weight factor deterministic. So we can get some two weight factors, each for Alice and for Bob, and then we compute the aggregate public key again using the weight factor. And then we're gonna make the signature using this aggregated public key. So challenge becomes something, and then to the signature, you should multiply your weight factor to your private key times challenge value. So if then we can effectively prevent the key cancellation attack, and also we can complete the Schnorr signature between two parties. Actually, we can do that between multi-parties more than two, but I just want to introduce the multi-party signature completion between two parties for now. And then I just want to introduce the detailed sequence of how the Schnorr sequencer should work like. The first step is the sequencer should do the proof of stake. So with the proof of stake, the sequencer will get slashed if the sequencer doesn't put the transaction into the given index. So here we can say private key of the sequencer is a KS, and the public key of the sequencer is large PS. And then for its next step, user creates a random nonce small R user, it's just completing a Schnorr signature together. So compute the public nonce, large R, and the user's public key is PU, and hash of the message the user want to send to the sequencer is M. We give these values, large RU, public nonce, and public key, and the hash of the message to the sequencer. Then, now sequencer can compute the challenge value before they have the exact detail of the transaction. And also before they get the partial signature from user. So if the sequencer can compute the challenge value E, so sequencer creates its own partial signature and returns the value to the user. And when the sequencer creates a partial signature and computes the challenge value E, we tweak one thing here, that adding index value into this challenge value. So also hash the index of the transaction will be included into the hash function. So by giving this partial signature to the user, sequencer is now just getting committed to including that transaction into that given index. And then after user gets the partial signature from the sequencer, also the user completes its own partial signature and send it to the sequencer with the detailed transaction data. The reason why we share the transaction data here after we get the partial signature is to prevent the minimal math stuffs. So actually it doesn't prevent the math 100%, but I'm gonna explain that how we can mitigate the math in other way. But actually this is the minimal setup to mitigate the math here. So finally, user and sequencer both have the completed signature each other. So what they have to do is publishing the signature data to the data layer. So the data layer don't need to be always the layer 1 blob transaction. So people can construct their own network, and if they have enough data to execute the transaction, then they just can execute the transactions. And later, when the transactions, batch of the transactions are submitted to the layer 1 chain, then if the transaction is not in the given index, then people can do some challenge retroactively. So finally, the sequencer verifies the signature and completes it and publish it. So this is how the Schnorr sequencer works, and validation is also pretty simple. We can validation will be used for the challenge system, or maybe bundling these transactions or compressing this transaction into one ZK proof using signature aggregation. And validation is just validating we have both public key inside of this signature, completion or signature. So challenge will be like, it's a pretty descriptive, but simply if the sequencer doesn't include that transaction into the given index, then anyone who has the signature can submit a challenge, and then the sequencer will get slashed. Okay, so we finished all some theoretical part. Now let's go to what we can do with this Schnorr sequencer stuff. in my personal opinion, I think we can use Schnorr sequencer not only for the layer 2 sequencer, but also the bundlers for the account abstractions too. Because for the bundlers, the account abstraction stuff, maybe I guess sometimes some bundlers will have not done enough throughput. So maybe they need to give some commitment data to the user that, okay, your transaction will be at some time included in the layer 1 chain, but actually we are just collecting and bundling the transactions, so please wait a little bit more. So I guess Schnorr sequential logic also can be used for the abstract account abstractions bundlers. And also we can combine these with the zero knowledge proof together to just compress the signature data, obviously. But one problem here is to make a most efficient system, what we have to do is maybe tweak the hash function to compute the challenge value from SHA-3 or ECDSA to a more Schnorr-friendly function. And as I mentioned briefly that it cannot mitigate the math attack 100%. The reason is because the sequencer can empty a slot and then actually just complete the slot later. And then maybe people, if they do not have enough availability to the previous signatures, actually it can be kind of there might be some math attack problem. To mitigate the 100% cryptographically, we should use time lock puzzle here. We should use time lock puzzle, and it can also not 100%, but you can mitigate the math attack for the sequencer's scheme. Also, there are some other possible approaches. Another approach is just combining two ECDSA signature. So users just submit a transaction to the sequencer using MetaMask ECDSA signature, and the sequencer also gives back the sequencer's own ECDSA signature and combining it using ZKP or etc. But the problem here is not a problem, but Schnorr sequencer is twice lighter, and also it is much easier to implement and aggregate inside of the ZKP too. So maybe there might be some trade-off between the user experience that using the existing ECDSA key or creating another EDDSA or a Schnorr-friendly private key, but actually there are kind of some trade-offs. And also we can use a BLS signature, because I am just assuming that we have only one single sequencer. And I believe that decentralized sequencer doesn't mean a multiple sequencer. Actually, we can do some burn auction stuff, so we can still make a decentralized sequencer even if we have only one single sequencer. But if you just think about, okay, we have a bunch of sequencers, set of sequencers, then actually we can also get some BLS signature from all the maybe other validators to a given index of the transaction. But I don't think it makes sense, because if you have 10,000 validators, and if we should make sign to every single index, actually it is too much network traffic. So I don't think it makes sense. So the conclusion. This sequencer scheme is suitable for application rollups or maybe account abstraction bundlers. And also it can give an economical instant finality, and then so you can just execute the state transition instantly. But if the application is pretty sensitive to math, for example, AMM, like Uniswap, or which have a very high throughput, actually it might be a good solution to run the application on top of this kind of a structure. And we can use account abstraction and also zero knowledge proof for the scaling. Okay, thank you so much, Hirase. Yeah, my talk.
Okay, any questions? There? Please. So what's the size of the signature?
64 bytes.
Okay, please.
Thank you very much for the talk. Surveyor. It seems like a lot of L2s or rollups have decentralized sequencers on the roadmap. Can you just elaborate on what you mean by having a decentralized sequencer, but then having only one sequencer? I didn't really understand that part.
What was your question? I'm sorry.
Yeah, so do you mind elaborating on what you mean by having a decentralized sequencer network, but using just one sequencer?
Okay, so I just mentioned about the burn auction, which is like we are just auctioning for a given epoch to be a sequencer. So you should burn your stake to be a sequencer. So the highest burner will get the slot, will win the auction for the slot. So for example, if the network is generating kind of a 10 ETH of revenue for each epoch, then maybe I will burn like 5.5 ETH to be a sequencer. But for example, if I should be the sequencer, then maybe I can spend like 20 ETH to be a sequencer. So it's kind of a permissionless sequencer can be considered as a decentralized sequencer.
Okay, cool, thanks.
Any other questions? Okay, the one next row.
Thanks for the presentation. It was really great. You shared about Schnorr signature being used for account abstraction bundlers, and I was curious about like if it gets used for account contracts, like to be the primary way to verify the signature. What do you think are the trade-offs for using Schnorr for the signature verification mechanism for account abstraction smart contract wallets?
I just think that we can use both. So,
can you please elaborate a bit more? Like, what do you mean by both? Like,
so people can have their own smart contract account,
yes.
and then their accounts control public key is the Schnorr public key. Then bundler can just compress the Schnorr signatures and then execute the transactions.
Okay, yeah.
Yeah.
Thank you.
Thank you.
Any other question? Last one, if any. Okay, here.
Hi, thanks for sharing. I'm wondering during the research period, is there any other alternative that shares the merits of Schnorr signature scheme that may be applied on sequencer scenario like this?
I am sorry, I didn't understand your question. I'm sorry.
Is there any alternatives for the signature scheme, such as share the merits of the Schnorr signature, but not Schnorr?
Not what? I'm sorry.
Because the Schnorr sequencer use Schnorr signature scheme, and during the research period, does the research team found other signature scheme that can be applied on sequencer scenario?
Actually, they were just combining ECDSA signatures or using the BLS signature. But actually, the proof size and the ZK-friendly for stuff, I just thought Schnorr might be the best solution for this. Thank you.